And we are live. Good morning, all of you. Good afternoon or good evening, wherever you might be. Or certainly 12 o'clock our time, so just starting up on the afternoon. Before we jump into our lecture for today, let's verify that everybody seems to be pretty comfortable with the material that we've covered so far and that there aren't any questions. So I'll open questions right here from the get-go. Let's see, we've got Garrison here. We're just waiting on Terrence if he pops in. So let's pause for a moment and find out whether or not anybody has any questions about the material that we've been covering so far. This is all material from Chapter 8. The problem is it doesn't feel like it's any material from Chapter 8 because all we've done is we've done a lot of mathematical work and we haven't done any work with regard to any circuits. So it's pretty exciting to start doing some circuits work. No questions on anything? Okay. Just word to the wise, there are a few of you who have submitted a homework assignment for the complex numbers assignment. That's not a long assignment. Feel free to write multiple problems on each of your pages. So you don't have to worry about that. That'll be due this week on Friday. If you haven't done that yet, I'm going to give you some additional assignments for this week, but I'm going to help you through a handful of those problems, and some of them are not that difficult. I've sent you two different assignments. One, just to help you on these differential equations and working through the differential equations. I think what I'm going to do is give you some changes on some of those numbers if you haven't started those yet, just some of those initial conditions that will make solving the problems a little bit easier so that they turn out to be whole number answers versus some of the uglier ones that you can get in there, especially when it's easy. And then last night I sent an assignment that is an assignment on second order circuits. And today we're going to have an opportunity to jump into that and to look at that. So since there are no questions, I'm going to surge forward and start jumping into this development of the second order equation from the circuit. So that's what we're going to work on today. So you'll see a few tricks of the trade here. Again, this is part of some of the most challenging work that we'll do this semester. That doesn't make it really hard, but it is part of the most challenging work that we'll do. And the reason is because there are some variations to analysis techniques that we would normally use to solve these circuit problems, but we're trying to do something different. And there are a lot of things that go against the grain of what your gut instinct would tell you to do. So here's what I'm going to do. I'm going to start by doing an example, and we'll spend a significant amount of time just doing this one example here to figure out what the solution to this particular circuit looks like and how we work our way towards that solution. So let's draw a circuit that looks like the following. So let's just give it a source voltage V sub G. Don't worry about what that voltage is. V sub G is it's a function of time, and it is known. That's the way I want you to think of it. It is a known function of time. And then a circuit, we'll put a resistor here. We'll put a capacitor in the middle. We'll have another resistor. And then over here, we'll put an inductor. And I'm just going to give all of these circuit components values. So this one will be 1/4. It's a 1/4 farad capacitor. It's a half a Henry inductor. This will be a 1 ohm resistor here. This will be a 1 ohm resistor here. And then what I want to do in this circuit is I want to just label every current and every voltage. There's an I1. That'll be a V1 over here. Let's put over here. Let's call this I2. Let's call this V2. Let's call this over here V sub L. Let's call this current IC. And we'll call this VC. So I'm just going to label every current and every voltage so that you see that the entire circuit has elements that are labeled with at least a current or voltage across it or currents going through it. So the reason I want to do that is I want to show you that when we operate working on this circuit, we can get a variety of differential equations. Some are easier to get than others. So some are easier, some are difficult. But what I want to show to you is with regards to the differential equations that we can find, if we can solve for that variable, for that differential equation, then what we can do is we can solve for other variables in the circuit. So we just need to figure out which variable we want to solve for given which variable we are asked for. Okay, so this circuit, we can solve for this circuit a variety of different ways. And you would normally look at this and you would say, well, if I look at this from a nodal perspective, there's one node. And if I look at this from a mesh perspective, there are two meshes. But there's a breakdown in the node analysis where when you look at this, you say that there's one node. So I'm going to show you the node that you would see. That node would be right here. And you would probably label this node down here as your reference node. So let me just do that. And I don't want you to write this with me. I'm going to write this and then I'm going to erase it. So if we wrote this nodal equation, I would start by writing the following. So let's call this V sub C because it's clearly VC if I've labeled VC across that capacitor. So if we wrote this nodal equation, it might look something like the following. Well, that voltage right there is VG. So it might look like VC minus VG divided by 1. That's cool. Then we have this current right here, which we know is IC. And for now, I'm just going to write it as IC like that. And the reason I'm writing it like that is because I've got this capacitor. But we know how to write the current through a capacitor because this is nothing more than C times the voltage across the capacitor. And take that derivative. So it's C 1/4 times VC prime. So IC is equal to C dV dt. So that works, and that's nice. So I've got a VC in my equation. I have a VC prime in my equation, and that's what I want. I want the voltage V sub C, and I want the derivative of the voltage, and ultimately, hopefully, the second derivative. But look at the problem here. When we're over here looking for I2, for this current here, the problem is I have these two elements, a 1 ohm resistor and a 1/2 Henry inductor, and the problem is that I would need to write that in terms of like voltage, what? Voltage divided by the resistor? Well, it's not just a resistor. So if I put a voltage here, like V sub L, I could do that. So I could label that V sub L, and now it would be VC minus VL divided by 1. That would work. Okay, but we need something in between here. Why? Because otherwise, if I look at this branch here, this branch has a resistor and a capacitor. I'm sorry, a resistor and an inductor. Before, when we had multiple elements in a singular branch and they were not sources, we could add those elements together. But right now in our work, do we know how to add a resistor and an inductor? Do we know how to reduce a series resistor and an inductor into one element? Do we have anything in the work that we've done that allows us to take those two and combine them into a single element? And I think you all know that the answer is no, we don't. So we would indeed have to put a node here, and we can do that, but for this circuit problem, I'm not going to. If you want me at the end to go back and do that, I will. But I'm not going to because there's an easier way to solve this circuit. It's just not obvious because it doesn't follow the normal techniques that we would use. And so we're going to come back to this and we'll have an equation that looks really similar to this. But let's get rid of all of this because there is no singular element in which we can combine those two together. So here's what we want to do. And if you can remember this, is ideally, I'm going to write it over here. Ideally, You can't always do this. We want our variables in our circuit equations to be the continuity variables. So the continuity variables are what? Somebody tell me what continuity variables would be. Voltages across what?
Across capacitor.
Excellent. Voltages across capacitors. And second one?
Current through an inductor.
Thank you. Currents through the inductors. So if we can do this, you're going to find out through this example how it makes writing these equations much easier. So that would be our goal. Our goal is see if we can use the current through the inductor. So notice I2 is indeed the current through the inductor. I want you to note that. And then the voltage across the capacitor. So here's the voltage across the capacitor right there. It's VC, but VC is this node voltage. It's one of those node voltages. The problem is it's not the second one. So this nodal analysis would not work if we were to try to use the continuity variables. So what we're going to do here is something that we're not used to, and that is we're going to do a mixed mode analysis. That is, this mixed mode is, it sort of looks a little like nodal and a little like mesh. But deep down inside, keep in mind that nodal analysis is KCL equations and mesh analysis is KVL equations. So what I'm going to do is I'm going to write one equation, and the equation I'm going to write for a nodal perspective is an equation at VC. So now let's try this. And remember, in this equation, we want everything to be in terms of, obviously, independent sources. That is always true. But I want it to be in terms of voltages across capacitors, currents through inductors. So here we go. The first part is going to be the same. VC minus VG divided by 1. Okay, so that's that current. This is a KCL equation. It's not a nodal equation. This current right here, it's IC, but we know that IC is 1/4 VC prime. And then we have this one, which we've labeled I2, but I2 is the current through the inductor. So we want to use a current through the inductor. So here we go. Plus I2. I sum those up and they're equal to 0. So notice the only variables in this equation are the variables VC and I2. Those are the only variables. VG is not a variable. VG is an independent source. We know its value. I'll tell you at the end what I want the source to be. Okay, so it's the value of that independent source. Okay, now the question is, where do I find a second equation that involves these two variables? And that is right around this loop here. So as I write that equation, so this is at this VC node, and this one is at this loop, I'll call it L1. So there's L1. So as I go around that loop and I write my equations, here we go. Minus VC plus V2, but don't forget V2 is I2 times 1. So I want the variable I2 in there. I don't want V2. So 1 times I2, and now I have VL, but I don't want VL in there. But we know what VL is. We know VL in terms of I2. What is VL in terms of I2? VL in terms of I2? Current voltage relationship for inductor? LDIdt, V is equal to LDIdt. So VL is the voltage. It's L 1/2 didt. What I? The I going through the inductor, that's I2. There it is. Sum those up. Those voltages are equal to 0. So we've got this mixed mode analysis that is allowing us to be able to write two equations, and those two equations are in terms of VC and I2. Now let's just go back to the circuit for a second. So I am going to want either a differential equation for I2 or a differential equation for VC. How do we know which one we want? It depends what we're solving for. So let's take a look at V1 in the circuit. Everybody see V1? I'm going to circle it. There's V1. In terms of VC or I2, can you figure out what V1 is equal to? I'm just going to jot these things down. Let me shrink this a bit so we can see this all. So V1 equals VG minus VC. Okay, so I can find V1 in terms of VC. VG is a known quantity. So if I were asking you to solve for V1, don't worry about finding a differential equation for V1. Just get the differential equation for VC, solve for VC, and then subtract it from VG, and that'll give you V1. Okay, what else? What if we wanted IC? What if I wanted IC? What's IC? Well, we know it's 1/4 VC prime. So as long as I have VC, I can take the derivative of VC and I can find IC. So if I wanted IC, I would still look for a differential equation for VC. All right, what else do we have? Well, VC, that's obvious. So far, taken care of, taken care of, taken care of. What about I1? What's I1 equal to? Well, I1 is equal to V1 over 1. Okay, well, V1 is VG minus VC over 1. Again, it's in terms of VC. Check. Beautiful. So we can solve for I1. What about I2? I2's in our equations. Perfect. What about V2? V2 is equal to 1 times I2. Great. As long as so if we wanted V2, we'd get the differential equation for I2. We'd solve for I2, and then we'd multiply by 1. That's really easy. What if we want V sub L? Well, V sub L is equal to 1/2 times I2 prime. So we get the differential equation for I2. So we can solve for every current and every voltage in this circuit. It doesn't matter which current or which voltage it is, by solving for either I2 or VC. Okay? So it doesn't matter which one it is. We can solve for any variable in the circuit. No matter which one it is, we can solve for either one of them. So let's show you how you would solve, or how you would first get the differential equation for either I2 or VC. Now, this is where your instincts and your reactions are going to be incorrect. So when you look at these equations, you look at this first one, and it looks like, oh my goodness, it seems like I've got a VC in there and I have a VC prime in there. So it looks like if I could just substitute for I2, I would be golden. Okay? But it doesn't work that way. It's the other way around. So what we really would do instead is this first equation, I'm going to work here, and then I'll work over here. So regardless of which path you take, you'll see both ways to do it. Okay, so if we're working over here, I solve for I2. I2 equals, now I'm going to bring I2, so I'm going to bring everything to the other side of the equation. So that would be VG minus VC over 1, which is obviously just VG minus VC. I'll write that in a second, minus 1/4 VC prime. So let's just rewrite it. I2 equals VG minus VC minus 1/4 VC prime. Now, you don't know this yet, but I do. You're going to need more than I2. You're probably going to need I2 prime. And I know we do, so let's just calculate I2 prime. Well, I2 prime is real easy. It's just VG prime minus VC prime minus 1/4 VC double prime. And that's where the second derivative comes from. So if I am going to want a differential equation in terms of VC, I'm going to take these two and I'm going to substitute those over here. Okay? So let's do that. Let's stay along this side and then I'll scroll back up. So staying along this side, I have minus VC plus 1 times I2. VG minus VC minus 1/4 VC prime plus 1/2 I2 prime. I2 prime, right above me, here's I2 prime, VG prime minus VC prime minus 1/4 VC double prime. Okay, and I add all of those up, and what we see is, on this one, this is equal to 0. Okay? So what did I do? I just took I2 and I substituted it in here. I took I2 prime, I substituted it in here, and I left VC by itself because now I have a differential equation that's just in terms of VC. Let's continue to clean up this differential equation. Let's work with it. So I'm going to put these in order. So the VC double prime, I'm going to put that first. So there's a minus 1/8 VC double prime. So took care of that term. Okay. Here is a minus 1/2 VC prime. Here's a minus 1/4 VC prime. So minus 1/2 is 2/4, and another quarter that's going to be minus 3/4 VC prime. So it took care of that one and that one. And then I have minus VC and minus VC. Minus 2 VC, took care of that one and that one. And now I'm going to bring the VGs to the other side of the equation. So when I take this to the other side, this first one, I get minus VG. And when I take this second one to the other side of the equation, I get minus 1/2 VG prime. We're almost there. So I don't know why I wrote this as a V2, so please forgive me for being a moron. So that is not V2. That is obviously VC. Okay, tell me what the one next step is to get this equation the way we want this equation. What's my one next step?
We need to get rid of VG prime.
Okay, no, this side over here all stays that way.
Oh.
We don't try to get rid of anything. Here's the key. Look here. What do I want this number to be? Differential equations we've worked with. What do I want that number to be?
1.
1.
Excellent. So I'm going to divide through the entire equation by negative 1/8 or multiply by minus 8. So I'm going to multiply by minus 8. They're both the same thing. VC prime plus 6 VC plus 8 times 2, 16 VC. Get my VCs, don't drop those C's. Equals, don't forget I'm multiplying by negative 8 VG plus 16 VG prime. This line here that is underlined right there, just remind you, that's the forcing function f of t. F of t, remember, it's a function of the sources. And in this case, surprise, surprise, it's not just the source by itself. It's 8 times the source plus 16 times the derivative of the source. Oh, my word. Unbelievable. That's the forcing function. So,
shouldn't it be 4 times?
I'm sorry. Go ahead. Yes, it is. Thank you. It's times 8. It is 4 times. Thank you very much. Okay, so we have our first differential equation, and this is a beauty. Box that up. That is generally the hardest thing to get. Once we're here, and you're going to see this when you start working on that differential equations assignment I gave you, working from here is fairly trivial. It's just mathematical procedure. Okay, so that's one of them. That is the differential equation for VC. So hold that. Now, this is what I claimed last week. Every differential equation, every circuit element, I don't care which one it is. I don't care if you're looking for I2. It's every current and every voltage for every circuit element are going to have the same exact thing. So when we do our work, we are going to expect the following for, what did we say our other variable was? I2, correct? Yes, I2. This is what we're going to get. Over here, we're going to get I2 double prime plus 6 I2 prime plus 16 I2 equals, and over here, I don't know what this is going to be, but I'll just call this like G of T. It's going to be a different function. It is not necessarily going to be this, and I doubt it will be that. It'll be rare that it's going to be the same. It's going to be a different function. So we're going to get that differential equation and see what that function is. Let's go back up here in order to do that. And so this time, what we're going to do here is, notice I want a differential equation for I2. It looks like, oh my God, I got an I2, I have an I2 prime. All I have to do is substitute for VC and I'm going to be done. But it doesn't work that easily. So what we're going to do is we're going to get VC here and solve for VC, and then we're going to plug in VC and VC prime into this equation on this side. Here we go. Solving for VC. Bring VC to the other side of the equation. VC is equal to I2 plus 1/2 I2 prime. I'm going to need the derivative. VC prime equals I2 prime plus 1/2 I2 double prime. One of the things that might cause you to be slightly confused, I've always gotten rid of denominators. Dennis, why are you not multiplying through by 2? Because I want VC, so I can substitute VC and VC prime over here. I don't want 1/2 VC and 1/2 VC prime. Okay, so I'm going to substitute in. Remember what the equation is. So as a reminder, it's VC minus VG plus 1/4 VC prime plus I2 is equal to 0. Here we go. We only have a little bit of room here. I'm going to get that in there. VC, I2 plus 1/2 I2 prime minus VG. Here's what I'm going to do. Everybody agree this VG is going to go on the other side of the equation? I'm going to hold it off. I'm going to bring this over here. So I'm going to hold it off. So I have plus 1/4, now VC prime, I2 prime, plus 1/2 I2 double prime. And then I have plus I2 equals, there's my VG over there. Okay, 2 more steps. So, darn you. Okay, so the first thing to do is my I2 prime. So here we go. I'm going to slide it in over here. So I have 1/2 I2 prime times 1/4, 1/8 I2 double prime. Double prime. Now the single prime terms, 1/4 and 1/2. Those terms sound familiar? Isn't that amazing? So that's going to be 3/4 plus 3/4 I2 prime. Then I have an I2 and an I2 plus 2I2 is equal to VG. Same thing. We're going to multiply by 8 this time, not -8. When we have I2 double prime plus 6 I2 prime plus 16 I2 is equal to 8 VG. there's our second equation. And I just want you to note that this side of the equation has the same exact form as this one here. Now I'm going to put in what is G of t. We know what G of t is. We just solve for it. It's 8VG. So notice here, G of t is equal to 8VG. Different function. But amazingly enough, it's the circuit elements that dictate what the form of the left-hand side of that equation will be. The circuit elements dictate that it will be the same form. Okay, so we know that we can solve for whatever we want in the circuit as long as I can solve for either I2 or VC. So let's do the following. Let's pretend this is a circuit, and let's solve for I2. I want to solve for I2 of t, and for the following conditions. Let's let VG equal 3 e to the minus 2t. Let's also let I of 0, let that initial condition be 10, and let's let V of 0, the initial condition there, equal to minus 4. So we're going to put some new pieces of information together for all of this to figure out how we use that. Because ideally, for the initial conditions, we would like, this is I2. I2 of 0 is 10. Ideally, we want 2 initial conditions for I2. But I gave you an initial condition for I2 and V sub C. Let's make sure I have both of those, I2 and V sub C. So we'll see what we need to do with those initial conditions. So let's first go to the differential equation, I2 double prime plus 6I2 prime plus 16I2 equals 8VG. There's VG. 8 times that is 8 times 3. That's 24 e to the minus 2t. All right, that's a differential equation. We're going to solve for I2. What's the first thing that I should do? Here's my differential equation. Somewhere I have I2 at 0 equals 10, but I need I2 prime at 0. And I don't know what that is because that was not given. So that means, to me, that means I need to use this to be able to find I2, well, that and this to find I2 prime at 0, and I'll show you how we do that. It's not hard, it's pretty easy. Okay, back to this big star. Like, wow, we found the differential equation. That was awesome. All right, what do we do with it? We found it, what do we do with it?
Find the homogeneous solution.
Outstanding. Find the homogeneous solution. So to do that, I need the characteristic equation. Here we go. S squared plus 6s plus 16 is equal to 0. Okay. How good are we at factoring? Good or bad? We're not sure. Okay, not too sure, so let's go ahead and do this. So if we factor this, if you're not sure, let's factor it. S1 and 2. If you don't see an easy factor, minus 6 plus minus the square root of 6 squared minus 4 times 16. All divided by 2. Minus 6 plus or minus square root of 36 minus, what do we have? 64? Okay, so what situation are we in? Looking at that. This is what?
Category 3.
I missed that, Jack?
Category 3.
I'm having a hard time understanding you. Are you saying -3? Is that what you're saying?
Yeah, I was saying we're in category 3.
Oh, thank you. Category 3, complex conjugate roots. And what do we have underneath this radical sign? Square root of what? So I already pulled out the -1. That's my J. And what's left? Square root of 28? Is that the square root of 28? Did I do my math correctly? Okay, divided by 2. So let's see, square root of 28, that's equal to -3, plus and minus. Don't forget, the square root of 28 is the square root of 7 times the square root of 4, which is 2. And that 2 is going to cancel with that 2. So -3 plus or minus J root 7. Ugly, whatever, we'll deal with it. Yeah, it's ugly, big deal. So that means that our homogeneous response is the following. I2 equals K1 times sine of the square root of 7t plus K2 times the cosine of the square root of 7t, all times e to the -3t. And that's just the homogeneous response. So I'm going to write that. Homogeneous response, I2H. Are we done with the homogeneous response right now? Yes or no? %50 chance.
Yep.
Yep, we are done with it right now. Everybody knows that there are two constants in there, but we leave them until the end. So right now, hold on to that. We'll underline it so we can find it when we come back. Okay, next step.
The forced response.
Excellent. Guess. So we're going to guess that I2F equals. Now, we're looking here. And the first thing we're doing is we're checking down here to see if there's a term that's just an e to the -2t. I'm going to tell you right now so you know, because we might not see this again. If this was a 2 here, this still does not have the same form, because the form of this is sine of something times e to the -2t. Okay? So if this was a 2, it wouldn't matter. So this form here is not the same as this form, so we're not worried about excitation at a natural frequency. So what's our guess going to be?
AE to the
E
minus
to the -2t.
Beautiful, both of you. A, e to the -2t. What else do we need immediately right now? First derivative, -2a, e to the -2t. You're going to love when we have exponentials. They're really easy. Exponentials here and constants are real easy. And I2f double prime equals +4a e to the -2t. Take these three, substitute them into the differential equation. So a reminder, here's the differential equation. Double prime plus 6i2 prime plus 16i2 equals 24e to the -2t. Okay, I2 double prime, that's that term, 4a e to the -2t plus 6 times that term minus 2a e to the minus 2t plus 16 times I2 a e to the minus 2t. Add all of those up, and that should be equal to 24 e to the minus 2t. 4a minus 12a plus 16a. 4 and 16 is 20. 20 minus 12 is 8. 8a e to the minus 2t equals 24 e to the minus 2t. Match coefficients. Match coefficients. 8a is equal to 24. A equals 3. So we have solved the forced response completely. The forced response, not IF, I2F equals, remember, there's my guess right there. I'm just plugging A into my guess. 3 e to the minus 2t. So now we're ready for the complete response. So the complete response is I2 equals I2F plus I2 homogeneous. And that's equal to 3 e to the minus 2t plus, see if I can recall it, k1 sine of square root of 7t plus k2 cosine square root of 7t all times e to the minus 3t. I remembered all that correctly. Okay, now is the time that we have to work on these constants, K1 and K2. Now's the time to work on the constants. So we're going to need I2 prime. So I'm just going to calculate I2 prime right now. So I2 prime is equal to, it's going to be a little bit of an ugly mess because of this sine and cosine and this quotient rule going on here. But whatever, we're tough, we're going to deal with it. Here we go. The derivative of 3 e to the minus 2t, negative 6 e to the minus 2t, plus. Now, the derivative of this, again, this is a product. This is the first term. This is the second term. So it's the derivative of the first. You ready for this ugliness? Here we go. Square root of 7, k1, cosine square root of 7t minus square root of 7 k2 sine square root of 7t. All of that, that's the derivative of the first times the second plus the first, copy it down, k1 sine square root of 7t plus k2 cosine square root of 7t times the derivative of the second minus 3 e to the minus 3t. All right, that's all of it. We're going to think of this minus 3 as just being right with this and this. It multiplies both of those. And I'm going to group everything together. It's a long equation here, but we're good. I2 prime equals minus 6 e to the minus 2t, okay, plus. So first, the sine terms. Minus 3 k1, minus 3 k1. That multiplies the sine. Up here, I have minus root 7 k2, minus root 7 k2. All of those multiply the sine of the square root of 7t, and outside of the big brackets, that'll multiply e to the minus 3t. Now the cosine terms, plus cosine. So here I have root 7k1, root 7k1. Here I have minus 3 times this one, k2, minus 3 k2, all times cosine of root 7t, and all that in brackets, and then times e to the minus 3t. So it looks ugly. It is kind of ugly, but it's all right. We can deal with it. So here's I2 prime. So hold those. And now what we need is we need I2 at 0. Slide back. I2 at 0. We have that. It's given. Given. We need I2 prime at 0. Okay. So we need to write another equation. And so let's scroll back here. And I'm going to tell you the way we find I2 at 0 is, or I'm sorry, I2 prime at 0 is by using this equation that we wrote. They come from the circuit equations. So I'm going to do it right up here. I'll do it here. You can do it down below. So right now, I'm going to analyze this equation for t is equal to 0. So for t is equal to 0, I'm going to write real small, minus VC at 0 plus I2 at 0 plus 1/2 I2 prime at 0 equals 0. All right, I'm going to clean up this middle section. I'm going to clean up this middle section and rewrite this equation right here in this middle where you can see it a little bit better. So we know what these values are. We have these values. So look at I2 at 0. I'm going to write this all the way over here where there's room. So I have, if I multiply by 2, I'll get I2 at 0. I2 prime at 0. I2 prime at 0, multiply by 2, equals twice VC at 0 minus twice I2 at 0. Okay? So we have VC at 0 and we have I2 at 0. I'm going to scroll back and forth, make you dizzy. We have VC at 0. Where did I give it to you? Right here, VC at 0, -4. I2 at 0, 10. We're going to substitute it. VC at 0, -4, right? That's what I said, -4, -4. Equals 2 times -4 minus 2 times 10. So I2 prime at 0 equals -8 minus 20, minus 28. By the way, just so you know, the units of that, amps per second, minus 28 amps per second. Okay, let's come back down here. So we wanted right here. What is this equal to? Minus 28. So we have 10. I2 at 0 is 10. I2 prime is minus 28. Pull this down a bit. Right there. I2 at 0 equals 10 equals. Now, plug in t is equal to 0 in this equation. T is equal to 0. There, I get the exponential e to the 0 is 0. So that's 3 times 0. That's 3 plus sine of 0. Sine of 0 is 0. Cosine of 0. Cosine of 0 is 1. So this just gives me a K2. And then e to the 0 is 1. So that just gives me a K2. Wow, that was awesome. 3 plus K2. Unbelievable. I can immediately solve for K2. K2 is equal to 7. See, that wasn't so bad. Now, I2 prime at 0, we said that's equal to -28. And that's equal to, from this equation here, this equation, it's equal to -6. Now, sine of 0 is 0, so that's all gone, that term. But here, cosine is 1, so it's going to be this out in front. So it's going to be plus square root of 7 K1 minus 3 K2, all of that obviously times this evaluated when t is 0, that's 1. So, all right, it's an ugly equation, whatever. So K1, we have a value for K2. So right now, I know if I bring this -6 over and I add 6, I'm going to have -22. And then I'm going to bring this 3K2 over to the other side as well. So plus 3K2, but we know what K2 is. K2 is 7. Oh, that's interesting. Equals square root of 7 times K1. So minus 22 plus 21 is equal to -1, and that's equal to root 7 times K1. That's easy to solve for. K1 equals -1 over root 7. For those of us that don't like radicals in the denominator, that's equal to -root 7 over 7. Beautiful. I have K2, check. I have K1, check. Here's the complete solution. I2 equals I2 all the way up here. It's equal to, right here, this equation. I'm just going to plug in my K1 and my K2. So 3e to the minus 2t, 3e to the minus 2t, plus K1. K1 is -root 7 over 7 times sine of root 7t plus K2. K2 is 7, and that multiplies the cosine of root 7t. All that is multiplied by e to the minus 3t. This is a current. It is in amps. Okay? So that is the solution. And we can go back and we can find the solution for VC. We can find the solution for any of the variables in this circuit, because as long as we can find I2 and VC, we already showed earlier that we can find any other solution. I want to go back to this here and remind you that right here, where did I put it? VG, the source, all the way back to the circuit. Here's the circuit. This source right here is equal to what I said in this example. I'll let the source be equal to 3e to the minus 2t. Let's just write that up there right now. So this is equal to 3e to the minus 2t. A long time from now, what's the value of the source when t gets large? What's the value of that source when t gets large?
3.
When t goes to infinity, what's e to the negative infinity?
0.
Good. So this VG goes to 0 as I'll call it at t is equal to infinity. When t gets large, it goes to 0. So I have no source. What would I expect all my currents and my voltages in this circuit to be if there's no forcing function there? The value of the voltage source is 0. What do I expect everything else to be?
0.
Excellent. Let's check if that happens when t is really large. When t is really large, that goes to 0. That goes to 0, and it doesn't matter what these things do. They're sinusoidal, but they're doing this. So they're going to 0. This first term is doing this. So a long time from now, everything has gone to 0, and there's nothing hanging around. Kind of interesting. Okay, I'm going to put our record on pause. We'll take ourselves a good 5-minute break, catch a breather, and then we'll answer any questions that you might have and see how we're doing at this point. So let's just pause the recording right now. I'll catch you back in 5 minutes. Okay, I'm back. How are we doing with that material?
I'm good.
Anything in there that was challenging, or do we feel pretty confident that what we needed to do with that was pretty much what we've done before? The difference is we're getting a differential equation, and so the analysis of getting the differential equation is a little bit different just because of that mixed mode method that I used there. I will tell you that it's not always going to be a mixed mode method. For example, if we had two inductors in the circuit, in that particular circuit, if we had two inductors and we had one in each of the loops, I think that probably would work out pretty nicely by just doing straight mesh analysis on each of those loops. We could go back and take a look at what would happen if we did both mesh analysis or nodal analysis, but the process just gets a little bit uglier. But you could do it if you wanted to. You could do the one node here that we pointed out and another node here, so we could do nodal analysis. Or we could do this mesh analysis here and this mesh analysis here. If we did the mesh analysis that way, what would happen is when we got to the capacitor and the inductor, if we're doing either mesh or nodes, in one of those we would get the integral rather than the derivative. And the beauty of this method here that I mentioned to you, of trying to use the continuity variables, is when you use the continuity variables, you never end up getting the integrals. You don't end up getting the integrals. The integrals can be a little hairy when it comes to the initial conditions in the equation. They can be a little hairy, but as long as we're using the initial conditions and keeping that with the integral, then we should be all set. Okay, so let's scroll through all of that and let's continue to work our way. So, did anybody have an opportunity to look at the material that I handed out, that I disseminated to you via email? Look at that differential equations sheet. Anybody look at that?
Yeah, I looked
Yeah,
at
I
it.
did a little bit.
And so were all of those pretty straightforward, or did anybody try some of them and have difficulty with any of them?
I thought they were all right, but
Did you get excitation at a natural frequency in there somewhere?
I've not done all of them. I just looked
Okay.
over.
Okay. Excellent. Excellent. Jordan, pretty straightforward with those?
Yeah, I haven't really tried them yet, but I've looked over them a couple of times.
Okay, let's pick one or two of those, because I mean, all we're doing now is we're just putting all of these pieces together. So let's take a look at some of these, and one or two of them, and just get a sense of what's going to happen in our analysis. I'm going to make a modification. Let's start off by looking at number 6. So number 6 has the following. V is a voltage. V double prime plus 7V prime plus 10V is equal to 20e to the minus 3t. Looks a lot like the problem that we just had. All right, and I'm going to change the initial conditions for you here. So I want, let's see, V at 0 is going to be equal to 8. V prime 0 is 0. And so what we're going to do is we're going to solve for V of t. We'll find V of t. Okay? So when we're solving this is like the hard part is done. The circuit analysis part is done. And so, my goodness, if the circuit analysis part is done, all we've got to do is do the mathematical part. But if you can do the circuit analysis and can't do the math, that's no good either. So let's just focus on how to do the math here. So here we go. S squared plus 7s plus 10 is equal to 0. That factors nicely. S plus 5, S plus 2, equals 0. S1 and S2 are equal to -2 and -5. So V, the homogeneous response, is equal to K1 e to the minus 2t plus K2 e to the minus 5t. Save that. Okay, now we go into the forced response. We're going to guess that V forced is equal to, notice, e to the minus 3t, e to the minus 2t, e to the minus 5t. They don't have the same form. Neither of them is the same. So we're just going to guess A, e to the minus 3t. Vf prime is negative 3a, e to the minus 3t. And Vf double prime is equal to 9a, e to the minus 3t. So we'll use this, this, and this, and we're going to substitute it into our differential equation. Here we go. So the differential equation is V double prime plus 7V prime plus 10V is equal to 20 e to the minus 3t. V double prime, 9a e to the minus 3t plus 7. V prime is minus 3a e to the minus 3t plus 10 times v, and v is a e to the minus 3t. Add those together, and they should be equal to 20 e to the minus 3t. So 9a minus 21a plus 10a. 10 plus 9 is 19, minus 21, minus 2a e to the minus 3t equals 20 e to the minus 3t. Cancel, cancel. Minus 2a equals 20. A equals minus 10, not done. Therefore, the F equals minus 10 e to the minus 3t. Now, the complete response. So V equals VF plus VH, and that's equal to minus 10 e to the minus 3t plus VH, K1 e to the minus 2t plus K2 e to the minus 5t. And then I'm going to get the derivative right now because I'm going to need it. So V prime equals 30 e to the minus 3t minus 2K1 e to the minus 2t minus 5 K2 e to the minus 5t. All right, why do I need that? For my initial conditions. So we have the initial conditions, 8 and 0. V at 0 is 8, V prime is 0, 8 and 0. V at 0 equals 8. V prime at 0 equals 0. Equals. Okay, V, here's V. Plug in T is equal to 0. Minus 10 times 1 plus K1 plus K2. Here's this one. V prime. Plug in T is equal to 0. 30 minus 2K1 minus 5K2. Let's just take these two, combine them together, and get all constants on the other side. So the first equation, when I bring this over, it's going to give me 18. K1 plus K2 equals 18. This one, I'm going to bring 30 to the other side, but then everything's going to be negative, so I'll multiply by positive, and that's going to give me twice K1 plus 5K2, and that's going to be equal to positive 30. You can use whatever you want to. For me, it's just easier to see this as multiplying by minus 2. Multiply by minus 2 and then add. The K's cancel. And then 2K2, minus 2K2 plus 5K2 is 3K2. And that's going to be equal to minus 36 plus 30 minus 6. K2 equals minus 2. So we have K2. Then I'm just going to take this and I'm going to substitute it back into the first equation. So K1 minus 2 equals 18. So that means that K1 must be equal to 20. So there's my values, total answer, total answer. So D equals 30, nope, not 30, minus 10, either minus 3t, minus, gosh darn it, minus 10, either the minus 3t, plus K1, plus 20, e to the minus 2t, plus K2, minus 2, e to the minus 5t, and that is in volts. Okay. So solving these equations, the most difficult part about solving these equations, so is if you look through that homework assignment, if you look through it, 1, 2, and 3, you can do all of those on one sheet of paper. That's just get the characteristic. First of all 3 equations are only homogeneous equations. They're all set equal to 0. There is no forcing term. So there's only a homogeneous response. So those are pretty easy. You can do those pretty quickly, get the characteristic equation, find the natural frequencies, and then find the expression for the current or the voltage. 4, 5, and 6, I'm going to give you some different initial conditions for sure on those. I'm going to look at the others afterwards. I haven't looked at 7, 8, 9, and 10. But on all of those, what you have is first, number 5. On number 5, so on number 4, start with 4. 4 is still a homogeneous equation, but now you have initial conditions, so now you can solve for K1 and K2. Number 5, a forcing function is a constant. That's the easiest forcing function there is. Second, on number 6, it's the second easiest forcing function. That's an exponential. Then on 7, it is a forcing function that is a constant again. And then a constant, and then a constant on 8 and 9, and then an exponential on 10. But there are other little things that are in there that make it slightly different. So let's do one of 7, 8, 9, and 10. Anybody pick one of those? The first number here is the one I'll do.
9.
9 it is. So for number 9, V of t, we have V double prime plus 4V prime. That is equal to 24. Okay, so the initial conditions are V at 0 is equal to 4, and V prime at 0 is minus 2. And I didn't check over all of these to see if the numbers worked out well. I wrote them up, and then I wanted to get you something quickly, and now I've been going through them to see if I can get the numbers to work out better. That's why I've got some numerical changes for you. So while you're out there, on number 4, change I1 prime of 0 to be 3. I think that'll work out better. I1 prime. So on number 4, some homework corrections. Put this over here. Problem number 4, I1 prime at 0 is equal to 3. I think that'll work out better, unless I made a mistake. On 5, let's do V at 0 is 8. If you haven't solved these yet, V at 0 is 8. And V prime at 0 is 2. And then I just said on number 6, just change number 6 to V at 0 is equal to 8. Okay, now let's solve number 9. So this is an interesting one. So let's not forget on number 9, V double prime plus 4V prime plus 0V equals 24. So let's not forget that. Now let's go to our characteristic equation. S squared plus 4S plus 0 equals 0, characteristic equation. So we have S squared plus 4S equals 0. S times S plus 4 equals 0. And so S1 and 2 are equal to 0 and minus 4. that means the following. V homogeneous equals K1 e to the 0t plus K2 e to the minus 4t. I think all of you know that e to the 0t is equal to 1. So V homogeneous is equal to K1 plus K2 e to the minus 4t. Watch that, hold on to that, we'll need that. Okay, let's go to the forced response. So we're looking at this equation here, and we're noticing that the forcing term is a constant. So normally our educated guess would normally be, don't write it down, a constant. But look here, a constant is already in the homogeneous response. So we know if we put a constant in here, it's going to give us 0. It won't equal 24. So we need to modify and make a better educated guess. So what's that modification to the guess? We don't guess that VF is equal to A, we guess that VF is?
AT.
Beautiful, T multiplier. We just multiply by an extra T. So VF prime is equal to A, and VF double prime is equal to 0. This one's still pretty easy. It's not so ugly. Oop, put that back there. Okay, so we're going to substitute those three into the differential equation. So V double prime, 0. Well, let's just recopy the differential equation, make sure we have it. V double prime plus 4 V prime plus 0V, let's not even write it, we don't need it, equals 24. So V double prime, 0 plus 4 times V prime, A, equals 24. Wow, that was wicked easy. My gosh. A equals 6. A equals 6, and therefore, V forced is equal to 6T. Let's put it all together. V equals VF plus VH. VF, 6T, forced response, plus VH, K1 plus K2, e to the minus 4T. If you're staring at this right now, if you're staring at this, you're looking at this, you're saying, oh gosh, that's the constant term. That must be the forced response because it looks like this, but it's not the forced response because we have excitation at a natural frequency. That's why it's not. Okay, now our initial conditions, just a reminder, I'll pull them down again. We have our initial conditions are, and I may have written it incorrectly, but V at 0 is equal to 4, and V prime at 0 is equal to -2. Did I write that up above? Yep, okay, got it right up there. Okay. So here's V, we need V prime. V prime equals, oh, this one's not too bad at all. 6, derivative of K1, 0, and the derivative of K2 e to the minus 4t minus 4 K2 e to the minus 4t. This is easy, I love this. Here we go, V at 0, on the left-hand side, I use this value, is 4. Same thing with V prime at 0. On the left-hand side, use that value, minus 2, equals, all the way on the right-hand side, substitute 0 in for these equations, substitute 0 in. So for the first one, T is 0, that's going to give me 6 times 0, plus K1, plus K2 times e to the 0, e to the 0 is 1. So K1 plus K2 is equal to 4. The second one, substitute in 0, I get 6 minus 4K2. 6 minus 4K2, you can see how we can solve the second one very easily. Bring the 6 over to the other side. So when I do that, I get minus 8 equals minus 4K2, or K2 is equal to 2. Substitute into there. So then I have K1 plus 2 is equal to 4. Lovely. K1 equals 2. Terrific. Let's write the complete response. V equals 6t plus 2 plus 2 e to the minus 4t volts. Okay. So those problems on that assignment are not too bad. The next assignment, which I handed out to you, so I want all of these to be due on Friday. So handling these pretty easy, the complex numbers, they're pretty easy. But the last assignment, which I sent out, that has 6 problems on it, I want to get you going on some of those, okay? And so I want to help you to develop some of those differential equations because they can be a little more challenging depending upon the approach that you take. So number 1 is interesting and not too difficult. In fact, your textbook focuses on problems that are just like number 1, series RLC circuit, series RLC circuit. So number 1 can be done in a variety of different ways. Number 2, a little interesting one on number 2. Notice on number 2, I just want you to find the differential equation. Don't solve for anything, just find the differential equation, okay? And then 3, we're looking for find the complete response. And if you're finding the complete response there, it says because you're not given any conditions, you can't find the values of K1 and K2. So it'll be in terms of K1 and K2. Then the next 3 have values at 0 minus or values at 0. 0 minus and 0 are going to be the same thing for these circuits because there's no switch in them. So one more additional challenge that I could give you is to put switches in these circuits. And right now we're going to leave those switches out. Somebody pick any of those 6 problems and we will tackle working on one of those 6 problems right now.
Number 5.
Number 5. So number 5, notice immediately, everybody look at number 5. Do you see any dependent sources in that circuit? I'm sorry. Do you see any independent sources? Same answer to both questions. Any independent sources?
No.
No, there are none. So there's going to be no forcing term. The only reason we're going to get an answer for this other than 0, the only reason is because I gave you initial conditions for an initial current in the inductor and an initial voltage across the capacitor. So we'll have initial energy in the circuit, but that energy is going to dissipate out exponentially and then it'll be gone. So you can expect there'll be no forcing term. So we can expect that this only is a homogeneous part, but because I put energy into those elements at t is equal to 0, we will have a response that will decay away. Here we go, number 5. So our circuit looks like the following. 2 ohm resistor. And I will tell you, working these circuits to come out really nice takes a lot of time. So, and a lot of mathematics. So I could have made a number of mistakes in doing this. Some of these might be uglier than I think, and some may not be. I have not had a chance. I've just been rushing to kind of put these things together for you because I don't like what's in the textbook. Okay, so here's a V2, 8, a V1, V2. Okay, so in an I, current I. So I think I asked you to solve for V2, otherwise it wouldn't be in the circuit. So find V2 for t greater than 0 if I of 0, so an initial condition, I of 0 is equal to 4, and V1 of 0 is equal to 8. All right, notice I'm asking you to solve for this. And that voltage is not one of the continuity variables. But look what is. This current I is a continuity variable, and that current flows right through there. So we know, just as a reminder, V2 is equal to 8 times I. Oh my gosh. So if we get a differential equation for I and we can solve for I, awesome. Then if we can solve for I, we can solve for V2. So solve for I, then use the value of I to solve for V2 by simply multiplying by 8. So I'm gonna use this mixed mode approach then is what I'm gonna do. And this is pretty darn similar to the problem that we had already. So this one shouldn't be too bad. So I'm gonna use this mixed mode approach. If I were doing nodal analysis, that would be what I would do for nodal analysis. Okay, so we'll write an equation here. That'll give me those three currents there. So let's write that at this N1. So let's write that equation. Here we go. At N1. Notice the voltage across here is V1. Notice that. So this current right here, this current is nothing more than V1 over 2. So V1 divided by 2, that's the current going out, plus this current going out. But that current is 1/4 V1 prime. I equals C dV dt. This current, I'm going to leave it as I plus I, because it's the current through the inductor. So I have two variables, V1, it's the voltage across the capacitor. I have I is the current through an inductor, so I'm golden. So I have that equation, whoops, that was not too sweet. One. Okay, so that's my one equation, sum that up, it's equal to 0. So I'm going to leave that like that. Now I'm going to find the other equation. The other equation I can find by writing around this loop right here. So let's call that L1. And so writing around that loop, we're going to end up with minus V1 plus this voltage, but that voltage is 3I prime. And then the voltage across the resistor, I know it's V2, but I don't want V2. I want my variables I and V1. And so this is going to be 8 times I equals 0. So now we said we wanted the differential equation for I, solve for I. And it looks like I have my I prime. All I have to do is substitute for this. It looks like all I should do is substitute in, but it doesn't work that way. We're going to work this one and substitute into this one. Okay. So V1, bring to the other side of the equation, equals 3I prime plus 8I. I'll need V1 prime. You can see how I need V1 prime, and I need V1 right there. So V1 prime equals 3I double prime. There's my second derivative, plus 8I prime. And now substitute. Here goes. My substitutions, 4. That's not a negative, so let's make sure we get rid of that. So V1 over 2, so 1/2 V1. 3I prime plus 8I plus 1/4 V1 prime, 3I double prime plus 8I prime plus I equals 0. Let's group our terms together. 3/4 I double prime. Take care of that one. Plus 3/2. Took care of that one. And plus 8/4. Ooh, plus 8/4. 8/4 is 2, which is 4/2. All of that multiplies I prime. Let's kind of get that, clean that up a little bit. I prime. And then my I terms, it's just that one. Plus I equals 0. All right. Very good so far. Let's clean that equation up. Multiply by 4/3. I double prime plus. All right, so this number right there is 7/2. So I have 7/2, a little scratch pad over here, and I'm multiplying by 4/3. 14/3. And 0 times 4/3 is 0. Bummer, not so nice. Okay, as long as we didn't make any any mistakes in our equation. Let's see, did I miss something for 1/2? Hold on, I missed something. My mistake. Did I get this? 8/2. Did I miss this term here? Yes, I missed that term, right? I apologize for that. I can erase, so I'm going to do that. Apologize. Right here. Let's clean that up. Okay, so there was an I term. I get that one there. That I term, that's 1. And that I term is 4 more. So that's 5I equals 0. I apologize for that. So again, multiplying by 4/3, we have I double prime. This number is the same, right? 14/3. I prime plus 5. 5 times 4/3, 20/3. I equals 0. It's getting late and I'm getting sloppy. Okay, there's our differential equation. It's ugly, big deal. S squared. Notice there's only a homogeneous response. Everybody see that? There's only a homogeneous response. Before I go to this, let's do the following. Let's find, we're going to need the initial conditions for I, and we said, whoops. In case you're wondering why this is happening, 2 hours is about enough for this iPad. It's overheating. We've got some problems with this particular pad. It's not an iPad, Surface Pro. And so it locks up. So when I move the screen, it doesn't move, and then it moves like 12 seconds later. So we have this, we need I prime at 0. Which equation are we going to use? Equation 1 or equation 2 over here to find I prime at 0? Which equation are we going to use?
Equation 2.
Equation 2 it is. So here we go on equation 2. So I have V1 at 0, negative, plus 3I prime at 0, plus 8I at 0 is equal to 0. We have I at 0, we have V1 at 0. I at 0 is 4, V1 at 0 is 8. 4 for that one, 8 for this one. I'm sorry, wrote this in the wrong place. There we go. I prime 0 stays there. And this one over here is the 4. So 3, I prime at 0 equals 32 minus 8. 32 minus 8, 24. Bring it to the other side, minus 24. I prime at 0 equals negative 8. At least that number works out nice. So we have the two numbers we need. I at 0, which was, I at 0 was 4. And now I prime at 0 is 8. Okay, so let's hold those. We're going to need those. Okay, here's our equation. Not too bad. S squared plus 14 thirds S plus 20 thirds equals 0. Not sure? Always rely on the quadratic equation. So minus 14 thirds plus or minus the square root. We're going to get into some ugly math here. Bear with it. (14 thirds) squared minus 4 times 20 thirds. Let's put this with a 3 and a 3 there so that we have a 9 in the denominator. All divided by 2. Okay, so first things first. This is minus 7 thirds. That's that part. Now the ugliness, plus and minus. Now I can pull a 3 out of that square root because there's a 3 squared in the denominator. Now let's see what that leaves me with. So that leaves me with the square root of what? 14 squared, right? Am I right on that first part? 14 squared. So that's going to be 14 squared is 196 minus, now I have 20 times 12. And 20 times 12 would be 240. So you can see what condition we have, even though the answer is ugly, minus 7 thirds, plus or minus. Now let's see, 196, 44, gosh, that's ugly. So it's plus or minus 1/3 square root of, I'm gonna bring out the J right out front here, J, because it's negative, and then I'll put a positive square root of 44, still all divided by 2. Reminder, square root of 44 is equal to 2 root 11. So that 2 will cancel with that 2 in the denominator, and that's going to be equal to minus 7 thirds plus and minus J, and then we're still going to have the 1/3, the 2's canceled, so it's going to be root 11 over 3. Yeah, it doesn't bother me at all. Ugly? Sure. Doesn't matter. Not that bad. So therefore, it's category 3. Therefore, the solution for this particular problem for I, this is just I now. So I is equal to K1 sine square root 11 over 3 T. This is kindergarten work. Just put the right numbers in the right location. Plus K2 cosine. I didn't mean to trivialize it because I know it's not trivial, but I'm trying to make you understand that the work we're doing here is not hard work. There's a lot of hard work we're doing, but the work we're doing here is not the hard work. And then e to the minus 7/3 t. Okay, beautiful. Now what do we need? Well, we have I, we need I prime. I prime equals, here we go, you ready? Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first, square root of 11 thirds k1 cosine square root of 11 over 3t minus square root of 11 thirds k2 sine square root of 11 thirds t all times the second e to the minus 7/3 t plus the first k1 sine square root of 11/3 t plus k2 cosine square root of 11/3 t all times the derivative of the second minus 7/3 e to the minus 7/3 t. Let me just group those together for you in the form that we always wanted. So the first one will be the numbers that multiply the sine function. So this is k1 times minus 7/3. Minus 7/3 k1 over here, it's minus 11 minus root 11. This is ugly. I agree, it's ugly. Minus root 11 thirds k2. All that multiplies the sine of root 11 thirds t. Okay, the cosine plus the cosine. Here I have root 11 over 3 k1 plus, oops, that's a minus. Come on. There we go. Minus 7/3 k2 and all that multiplies the cosine of root 11 over 3 t, and then all of that is multiplied by this exponential e to the minus 7/3 t. 7/3 k1. Okay, got it all. I think I got it all correct. All right, so our conditions. So we have I at 0. I don't feel like scrolling this because it's not scrolling well. Anybody remind me what I at 0 was? That was 4. Is that correct?
Yeah, it's 4.
Thank you. And what was I prime at 0? 8 or negative 8?
8.
-8.
Negative 8.
Yep.
Okay. All right. From the equations now, always from the initial conditions, always from the equations. Okay. So from the equations. So this one, we're looking at this equation, we substitute in 0. Whenever we plug in t is 0, the sine is always 0, the cosine is always 1, so we end up with k2. And that's always beautiful. And then when I substitute 0 in here, it's just k2 times 1. So that's beautiful. It allows us to solve for k2 immediately. We saw that already. That happens all the time. For the second one, this term is going to be the 0. This is the mess that we get. So this is going to be equal to root 11 over 3 k1 minus 7 over 3 k2, and then it's times 1 times 1. Okay, so k2 from the first one, k2 is 4. So let's just plug this in the second one. So I'm bringing all of this over, k2 is 4. So I have minus 8 plus 7 times 4 over 3. K2 is 4. And that equals root 11 over 3 K1. And I know these numbers are ugly, but they're not. So let's multiply both sides by 3, minus 24 plus 28 equals root 11 K1. So it's a 4. Here we go. K1 equals 4 over the square root of 11. You don't like square roots in the denominator. It's equal to 4 root 11 over 11. Those are the numbers. I know they're ugly, but they're not. They're beautiful. So here's our total answer. So in this case, this was solving for I equals K1, 4 root 11 over 11 times the sine of root 11 over 3. Do I have that right? Root 11 over 3? Hold on, I gotta make sure I have my right numbers here. Come on, don't freeze up on me. Yes, root 11 over 3. T plus K2. K2 is 4. 4 cosine root 11 over 3t. All of that multiplied by e to the minus 7/3 t. Are we done?
Need to multiply by 8.
There you go. Going to multiply by 8. V equals 8 equals 32 root 11 over 11 sine root 11 over 3t plus 32 cosine root 11 over 3t e to the minus 7/3 t volts. And isn't that a thing of beauty? I know it seemed terrible, oh my gosh, but that really wasn't that bad at all. Just hang in there with the numbers. Don't let the numbers bother you. It's very difficult to make these numbers work out nice. You're going to end up with a lot of square roots. You're going to end up with a lot of things like that. Don't worry about it. Just grind through it. And if you need to, and if you want to, I want you to notice I never used the calculator to put in the square root of 11. I never did that. I just kept dealing with it. Just keep carrying it along. Okay, comments, questions? Any comments or any questions on that? Everybody feel pretty comfortable? Feel good? You loved it? You want to do 100 more? Yeah, okay, I'm not hearing the excitement. I'm not hearing the love right there. Okay, so the other 6, maybe we'll tackle one more tomorrow, and then we're going to move on. And this is what we're moving on to. We're moving on to a chapter in which all we care about is when the sources are, the independent sources are sinusoidal sources. And we know if they're sinusoidal sources, that the forcing functions are going to be sinusoidal sources. And there is a real nifty shortcut way of solving these problems that involves a high amount of complex mathematics. When I say complex, mathematics with complex numbers, rather than doing the differential equation. But when and if we compare the two, you will do the complex numbers any day over the differential equations. So we'll look at that tomorrow. Okay? If there are no questions, I will see all of you tomorrow. Stay safe, stay away from people. Things are getting worse, not better. Be smart. Send me your questions if you have any questions, your emails if you have any questions, send them to me via email. Otherwise, I look forward to seeing you sometime tomorrow. Take care. Have a great rest of your day, everybody.